Great. Okay, so I'm going to start today. What we're going to be talking about is we're going to talk about phase changes. That's our big thing we're talking about. And well, actually, we're going to talk about phase changes. We're also going to be talking about, so today is going to be about solubility, so what things dissolve in. And we're going to talk about phase changes. Okay, and they're two really different topics here. I want to introduce a term that we're going to talk about today, and it's called dissociation. So dissociation is things separating, okay? And so if I'm thinking about a dissociation reaction would look something like this. Whoops, not like that. Dissociation reaction would be something like A and B and they're stuck together. You know, and it might be able to come back and get stuck together. So I'm going to do a double arrow there. And then they separate to make A and B separate. So when we talk about dissociation reaction, that's what we're talking about. Okay. I want to add, so that's going to be important in terms of we can talk about things like when a salt dissolves, right? You have dissociation of those ions. So if I think about a salt crystal, let's say sodium chloride. What colors am I going to do? I'm going to do this. So I'm going to do sodium, and I'll do chloride. Okay. I picked the colors I did because what will happen in water, sodium chloride dissociates into its ions. So we could think about this reaction. And I like to, when I think of it, I like to do the ions like the colors that they are, or the charges like the colors they are in your car battery. Okay, so sodium and chloride can break up like that. And what's going on is sodium and chloride, when they come together to make table salt, right? When you look at table salt, what that is that's actually a crystal. And so it has an ordered structure. So I've got a sodium hydrogen there, and I'm trying to think of what I should do with my chloride ions. How should I draw that? It's chloride, so chloride minus versus sodium plus, which is bigger? Is that the chloride, right? Okay, we think about chloride minus, it has an extra electron, so it has the electronic structure of argon. Sodium plus, what does it have the electronic structure of? Neon, right. Okay, we take away an electron, and we end up here. So clearly argon is bigger than neon, so I should be drawing my chlorides larger. So I'll do that. And so if you look at a crystal of this is what it would look like. Your book has a better picture. I maybe should have pasted it in. And just imagine this going on and on. Okay? And so if we think, and it's also in 3 dimensions, so if we think about this sodium right here, there's a chloride out here in front of it, and there's a chloride behind it. So 6 around each of those. Lots of good interactions there. Before we talk about how it dissociates, let's just think about the strength of those interactions. Okay? So before we talked about intermolecular forces. Now, your book didn't actually put ionic bonds in there, okay? And the reason why your book probably didn't put ionic bonds in there is because these aren't molecules, right? They're ions. They're ionic compounds. But let's go ahead and add them kind of to our list anyway. What was our weakest intermolecular force? London forces, London dispersion forces. Okay, what was our next weakest? Or the next one up? Dipole-dipole interactions, good. Okay, And then what was there we go. And then what was our next strongest? Hydrogen bonding, which is kind of, we talked about that being an extra special strong form of dipole-dipole interactions. Okay. And so when we talked about these, we had this got stronger, right? Okay, what happened to our boiling point as we went this direction? Stronger interactions means higher boiling point. It takes a lot more energy to separate these things. And there's an underlying cause of these stronger interactions. What is that? As we go down, we have, it's related to electronegativity. It was charge, right? The amount of charge. These are all partial charges, but the partial charges get larger as you go from the top to the bottom. Okay, so these get stronger, the part charges get larger. So if I was to put ionic interactions in this list, where would I put it? The very bottom, because ionic interactions, these are full charges. Okay, so we'll go ahead and we'll add that. Okay, and these are super strong actually, because of the full charges. So ions, we think about boiling salt. Boiling salt is going to happen at something like, I think it's 3,000 degrees. I may be wrong, but it's thousands of degrees. Okay, as opposed to hundreds of degrees for water, right? And then lower and lower as we go back. So super strong interactions. Let's just remind ourselves or add charges increase. And so this concept of increasing charges, we're going to use it and we're going to apply it over and over again in chemistry to explain things. All right, so these ions, if I go ahead and I put salt and water, you know that water, it actually dissolves, right? The crystals go away. And what's going on is that these sodium and chloride ions are breaking apart from each other. And well, we can talk about the strengths of those in a minute. And what's really going on there is if I think about my chloride, right? I'll think about a chloride ion here. Is that water molecules are going to surround that chloride ion and they're going to interact with it. So we could imagine having a water here, and that water has an interaction with the chloride ion. Okay, we can call this, we've talked about these forces so far as being individual, right? We have all London forces, London forces with London forces, dipoles with dipoles, hydrogen bonds with hydrogen bonds, but we can actually mix these things up. And so, excuse me, we could have this, we could call this a dipole ionic interaction, okay, is what your book would call this. You might also call it a hydrogen bond ionic interaction, and I would just accept that, okay? But I'm going to write it down, I'm going to follow your book. Dipole ionic interaction. Why is your book calling this a dipole ionic interaction instead of a hydrogen bond?
Because the water molecule has a dipole, and because it's an ion, it's not just like a normal atom. It isn't forming a hydrogen bond. Like it's that mix between the two.
Okay, because it's an ion and it's not a regular hydrogen bond. It's not a regular. You said a regular atom. Which, I'm going to be even more specific. Which atom?
Nitrogen, oxygen.
Nitrogen, oxygen, or fluorine is the atom that has to be the acceptor, right? So let's go ahead and write that that definition down again. Okay, so hydrogen bonds form when a hydrogen on a, or bonded to, let's say, bonded to, and when I say bonded, I mean a covalent bond, bonded to an oxygen, nitrogen, or fluorine interacts with a lone pair of electrons on a oxygen, nitrogen, or fluorine. Okay? And just assume it's interacting with the lone pair of electrons if it's interacting with one of those. Okay? Despite, regardless of angle or anything based on how your book's treating it. Yes?
So I guess I have a question about like if it's a nitrogen, oxygen, or fluorine, like that molecule has to have hydrogen around it. Like it can't, can it be like a nitrogen bonded to a carbon and would a hydrogen bond still form if the nitrogen had a lone pair? Or does it have to have like hydrogen around it?
Let me make sure I'm understanding this. So you've got a nitrogen bonded to a carbon, let's say. So let's go ahead and do cyanide for that. That's a good example for us. We'll do this. Okay. So what am I doing with the rest of this again? Can you repeat that?
So like if you had like ammonia as another example, like
Right.
would hydrogen bonds form in both of those cases? I guess like the only thing I'm questioning is like because it says like hydrogen bonded to oxygen, nitrogen, or fluorine, so I'm just confused like
So
nitrogen has to have.
so this would be our hydrogen bond. This does not. Are you asking whether this has to also have a hydrogen on it?
Yeah.
It does not.
Okay.
Okay. Good question. So good question. Do you guys hear the clarification? This is a hydrogen bond here. Okay. This does not have to have a hydrogen bond. The acceptor of the hydrogen bond. I like to talk about this is a donor, hydrogen bond donor. This is a hydrogen bond acceptor. The acceptor does not have to have enough hydrogen. Yes.
Is dipole ionic interactions above or below hydrogen bonds?
That's a great question. So let's talk about that. So where would the strength, if we're going to mix these things, right? And we can mix anything, but if we have this right here, let's compare that. Well, let's compare that to water, right? So let's say instead we have this interaction. Okay. If I have this interaction, that's a hydrogen bond, which of those would be stronger? This or that? What do you think? Use charges to explain it.
I'm thinking the dipole ionic interaction is stronger.
You think this is stronger because?
The full charge of the chloride.
Yeah, because we have a full negative charge here as opposed to a partial negative charge. So we have full charges here, so this is going to be stronger. Okay, so this right here, this is stronger than an H bond, a hydrogen bond, or a dipole-dipole interaction. Okay, does that make sense? Great questions. Okay, so it's all about the charges. Okay, so that's how this chloride, that's why this breaks apart. It breaks apart because you actually get lots. You don't just have one water around this. You're going to get lots of waters around this. Why I keep putting two oxygens. You notice that I'm pointing the hydrogens at the negative charge because the hydrogens are going to be the positive part of the water, right? But you can imagine surrounding this with waters, and then surrounding those waters with waters, actually. You're going to get kind of a couple shells of effect. All right, questions?
Are you ever going to be forming, when you have a dissociation, are you ever going to, are the water molecules ever actually going to be forming hydrogen bonds with the ions? Because since the ions technically, like even with the ammonia example, like that's still a cation, right? So wouldn't it still form an ionic dipole interaction since it does have that full charge?
As opposed to calling it a hydrogen bond?
Mhm.
Yeah, so you would want to call this, so in terms of this, so the question is, what would I call this? Or it's related to what I would call this. I would call this I could call this either a dipole. Formerly, your book likes dipole ion interaction or dipole ionic interaction. I would accept hydrogen bond ionic interaction.
Okay,
Okay. Does that answer the question?
sort of.
Okay, can
Like, I was asking about like if you have a polyatomic ion that has a nitrogen in it or something like that, it would still be a dipole ionic interaction, not a hydrogen ionic interaction, right? Because it still has that full charge because it's an ion, right? Even if it
Oh,
does have
if
nitrogen.
no, I would call it a hydrogen bond, or I guess it gets mixed up. So you're saying, what if we have a polyatomic ion and we have a charge on the nitrogen or the oxygen?
Mhm.
What would we call that? And I think your book, I would accept it as a hydrogen bond. I would accept. I'm not looking to. I do want you to identify these. I'm not looking to mix them in a way that I'm trying to trick you, or there's something really technical. But when I think about what your book did, your book actually did, and maybe this is why you're asking, your book actually did this. So it deprotonated a water, and then it had another water next to it. And it called that a dipole ionic interaction. Okay, which I would accept. I would accept hydrogen bond there probably as well. I would accept a number of different things because I don't want us to get bogged down in what we're technically calling things. But what I would want you to be able to tell me is this stronger or weaker? I care much more that you understand the concepts than you can name things correctly. But there will be some identifying things. Which of these two is stronger, the top or the bottom? Score the bottom. Okay. How many people think the top is stronger? How many people think the bottom is stronger? Good, it's the bottom, right? This is stronger because we've got higher charge. That's what I really care about.
Okay.
Other questions? All right. Yes.
Oh, wait, so why was the Cl and H, why is that a hydrogen bond interaction? If the hydrogen bond was like
It's
an O and an F.
Yeah, it's technically not a hydrogen bond interaction. I'm telling you, I would accept it if you called it a hydrogen ionic interaction.
Oh.
Okay. Because I'm going to accept a broad range of things. Some things are obviously wrong, but mostly I care that you could kind of rank the strengths. Okay, let's see. Okay, so we're going to go on. I'm going to go on. I'm going to talk about solubility then. And in terms of solubility, I want to introduce a couple terms. Oh, it didn't like that. All right, solubility. So we can talk about, especially when we think about liquids, mixing liquids together, we can talk about liquids being miscible. Okay, and what we mean when we talk about things being miscible is that they dissolve in each other essentially. All right. And really often we'll be talking about something dissolving in something else, like salt dissolving in water. All right. And generally the thing dissolving in something else, the something else, there's more of it. All right. So I had coffee earlier today that had sugar in it. Sugar was dissolved in it because it was more water than it was, or sugar was dissolved in the water because it was more water than there was sugar. Does that make sense? Okay. And there's not really a hard and fast rule for that. Also, we can talk about things being immiscible, and things do not dissolve in each other. All right, so an example, the book likes the example, it talks about ethanol, which is drinking water, alcohol, and water. Those things dissolve in each other regardless of how much you're putting in, regardless of the amounts. And then things that don't dissolve in each other, you've probably seen oil and water, right? But oil and water, salad dressing, things separate out, you get two layers. So we can talk about oil that would be in salad dressing, or just oil. You could take gasoline and water and mix them together and you would get two layers. And generally in terms of solubility, we'll have some math, we'll do this later, but in terms of solubility, we have kind of a rule in chemistry that like dissolves like, okay? And what I mean by that is polar molecules are going to dissolve in polar molecules, or polar substances. Okay, and nonpolar substances dissolve in nonpolar substances. And what I want to do is I'm going to go polar, and I'm going to say ionic substances. Okay, ionic substances aren't exactly polar. You don't apply it the same, but essentially it's about charges. Things with a lot of charges dissolve in things with a lot of charges, and things without a lot of charges dissolve in things without much charges. Okay, so we've done the sodium chloride thing up above. We could think here about sugar and water. And I'm not going to do table sugar because it'll take me longer to draw, but we could talk about glucose, which is the sugar that's in your blood. It's the sugar that your liver is going to release for your brain. This is an example of glucose. Oops, that should be a carbon. When I started drawing it, I realized I was in general chemistry and I couldn't do it with lines. Each carbon has to have, it's just going to be a mess by the time I'm done. Okay, so that would be glucose that's in your blood, all right? And do you see it looks like water, sort of? There are a lot of OHs on here. Each of these could hydrogen bond. There's a lot of OHs there, all right? If instead it was, let's say if instead we had some hydrofluoric acid, which actually does stay together. I told you this is super dangerous, right? But that's also very polar. That would dissolve in all these things too. Okay. Glucose is actually a solid, so you need one of these to be a liquid. Questions on that? So an example, I'm going to do it in a different color over here. An example of a nonpolar substance would be like gasoline. So gasoline has octane in it. You've probably heard that, octane rating. It's going to have a bunch of carbons in it. I don't know which octane. I need 8 carbons here. I don't know which octane is going to be the right one. What have I got here? I've got 6 so far. Shoot, I'm just going to do this. 6. No, I've got what, 10? You guys need to help me out here. Lose 20 IQ points sitting up at the board. I can't count anymore. So you might learn about this later. I don't think we cover it probably later, probably have time to cover it later in the course. But when you talk about octane rating for gasoline, they want these highly branched. There's different ways I could connect these carbons. I could connect them all in a straight line, but that actually causes your car to knock. That causes the ignition to happen too early, and the car makes a booming, knocking noise. So your octane in your car is this highly branched carbon molecule to prevent that from happening. There's also a favorite molecule in chemistry, in organic chemistry, is benzene, that has this structure. Okay, and when we look at the two of these molecules, if we think about the electronegativity of carbon, that's 2.5. The electronegativity of hydrogen is 2.1. What's the difference there? So right, there's all carbons and hydrogens. What was that? 0.4. Is that polar?
No.
It's non-polar, right? So these are non-polar. These two mix together just great. I could take as much benzene, they're both liquids, as much benzene and as much octane, and I can mix them together and they both dissolve well. Okay? Does that make sense? All right, so like dissolves like. Now, we have some situations though. What do I do if I'm cooking in the kitchen and I get some oil on my hands? Let's say I'm making roasted asparagus and I decide that I just can't get it coated by trying to toss it with the spatulas, and I've got to get my hands in there. Now I've got oil all over my hands. How do I get rid of it?
Use soap, because the not-soap molecules have that non-polar part and a polar part, so they interact with the water and get stuck in your hands.
Right, so I guess I don't know if everybody can hear that, but I'm going to repeat it. We have, you're going to use soap, right? You guys know you use soap to get the grease off your hands or oil off your hands, and soap actually has a polar and a non-polar part to it, and that's how you get it to work in water. So we can talk about, some molecules have polar and non-polar parts. I'm going to say side, although it might not always be a side. It might be multiple sides. Yes, it has to do with what functional groups you have on it. I'll do an example of soap here. So a non-polar side and a polar side, your book doesn't use this term, so I'm not going to make you responsible for it, but I'm going to introduce you to it. These molecules are called amphipathic. You might also hear other terms for them. Okay, they have a polar side and a non-polar side. An example of one of these molecules. So they used to make soap by taking animal fat and you would treat it with lye. So you'd take animal fat and you have this O here. What the lye would do is it would take the H off of it. And you would get this sort of molecule. Just go through here, and each carbon has to have 4 bonds. Where you don't have 4 bonds, you're going to go through and fill in hydrogens. Hopefully better written hydrogens than I have. Okay, so if we look at this is an example of a soap molecule. I got tired. This is probably longer. So this is right now, I don't know how many carbons that is, but that it should be 16 or 18 or 20. Okay, if that was really an animal from an animal fat. And so this part of my molecule right here, that's all C's and H's, it's all nonpolar. And this part of my molecule over here, I've got a charge, right? Okay, so charge, definitely, this is polar. But charge next to a non-charge, the electron's being pulled this way. And so this nonpolar, if we think about washing your hands or something, this is going to be attracted to oil. Or it's going to attract oil, it's going to mix with oil, however we want to say that. It's going to dissolve in oil. And this part is going to be attracted to water. So when I get oil on my hands when I'm cooking, I put the soap on my hands, and the oil is attracted to this part of the soap, and this part is then attracted to the water, and so the water rinses down the drain and it pulls the soap along with it, which pulls the oil along with it. Right? That's the way you think about that. Okay. Now, it isn't exactly like these guys separate though, because this is nonpolar. It doesn't want to associate with the water. It doesn't want to be separated all out there. And so if we think about this, you may have seen this in a biology class, that we have a polar head. They'll do these little circles, and we'll have a nonpolar tail. I'm going to match my colors up here. So for soap, we're going to have one tail. All right. And what that can do is the head is bigger than the tail. And so what we get formed are these micelles. So if I think about one of these guys is, once again, this is my soap molecule. So it's a round head with a tail that will end up with, they'll form these circles or these spheres actually, where the outside, these are our polar heads and they're interacting with water on the outside. We're not really showing the interaction here. There's a lot more water than that. But these are interacting with water on the outside, and then on the inside, all the tails are in here hiding from the water essentially, if you think about it. And if I have oil on my hands, what's going to happen? The soap will do this. The oil, if this is oil, the oil will end up stuck in here, where it's nice and hydrophobic. Okay, so you can imagine this being oil.
Does that have to do with how we figured out phospholipid bilayers?
I'm going to go to talk about a phospholipid bilayer next, okay? But the same sort of thing happens with different molecules in terms of getting a phospholipid bilayer. So if we have instead, if we have a polar head and we have two nonpolar tails, you see that the nonpolar tails, at least in my cartoon, right, are about the same width as the polar head. And so now it works well that we can get this lipid bilayer, okay? And so we have a lipid bilayer from when we have those two polar tails, and this is like, we could think about this as being part of a cell membrane. Okay, and cell membranes are much more complex than this, all right? But this is a good place for us to be right now. This ends up being a great barrier for cells, right? For preventing things from preventing polar molecules from going in and out of the cells. All right, and so if we've got a water, let's just say water. I've got water here. Water comes up. Remember, these are polar. This is nonpolar. Water comes up to the membrane, and it's happy to interact with the outside of the membrane, but it doesn't want to go in here, so it can't cross. Okay, and the same thing goes for like sodium and chloride and other things like that. So cells will have proteins that are channels that are embedded in the membrane that will control how much things can go in and out, like water like sodium and chloride and things like that. Questions? Okay. When they design drugs, when they're trying to design pharmaceuticals, what they try to do is they try to make a pharmaceutical that is kind of on the edge between soluble in water and soluble in fat, lipid, whatever. Okay, soluble in oil. You try and make it as hydrophobic as possible, but still have it dissolved enough that it could go in your blood. Okay, and then you get it and you want to make it small so it can come up to this and it's okay being in here. And those are the sorts of pharmaceuticals that will cross the cell membrane on their own. Okay, so that's something when they're making drugs they're trying to do. Questions? Okay. All right, well, that is solubility. I'm going to move on to talking about phase changes. And phase changes are a lot of fun. I'm going to get to talk more about cooking.
Like, are we going to talk about solubility rules and all that, or is that all?
Well, we talked about solubility rules, like in general, right, in terms of in first term. So do we come back to it? But we will come back to it in terms of, we'll talk about how constants. So calculating how much stuff is soluble. And frankly, I haven't taught from this book before, so I don't know when it comes. Sorry, I can't tell you how long. Might be 2 days.
Okay, I wasn't here first.
Oh, okay, got it. Yeah. Okay, so let's start out with this. I've got a couple pieces of meat here that are being cooked. Which of these meats looks more tasty? The one on the left or the one on the right? The one on the left. Yeah, the one on the left definitely looks more tasty. I'm going to break talking about general chemistry and we're going to talk about natural selection. Okay, so look, in chemistry, we can explain most things using charges. In biology, if you want to explain why something is, usually it's natural selection, right? So natural selection is, well, you guys know what natural selection is? I'm not going to try to explain natural selection that much in here, but I want to explain it enough that you can tell your biology professors I was talking about it, and Jen can make them angry, okay? So, can we use, this, most of us think this looks more tasty than that, right? Why is that? Can you use natural selection to explain it? Let's go with somebody else. Okay, go ahead, give me an answer.
It has to do with the idea that, eating, well, that looks mostly raw. And eating raw meat obviously has a lot of health risks associated with it. And probably most people got sick when they originally ate it. Like in primitive days, they, killed an animal, went and ate the meat without, cooking it. And then over time, they realized that made them sick. And eventually all the people that it was appealing to died off. And so now it's just a natural instinct that the thing that's healthier for you and that isn't going to kill you is the thing that's more appealing.
Right. So I'm gonna restate that briefly, but that's good. That's exactly one of the reasons that we would think about. So your ancestors liked this sort of meat. Okay, they like meat that looked like this and not like this. When there was a mixture of humans that liked this meat and that meat, the ones that ate this meat were more likely to get food poisoning, right? You kill an animal, you don't eat it all at once, you store it someplace, it starts going bad. You keep eating it, and if you're cooking it, then you're cooking the outside of the meat where the bacteria are growing and you're killing them off, right? You're less likely to get food poisoning and either die from that or die from something that you're slowing down because you have food poisoning and something else gets you. But so that's one reason. Another reason actually is that this meat like this, when this is cooked, what happens is the proteins break down more and you can get more nutrition from them. Okay? So the thought is that you wouldn't have to kill it, you could make it through harder times because you were getting more nutrition from the meat that's actually cooked. So there are reasons for liking one versus the other. Okay. What I want to talk about, though, is what is this stuff? So we get this brown stuff and we like it, right? What is the brown stuff that happens when you cook meat? Okay. And what this is this is something called a Maillard reaction. It's the products of a Maillard reaction. So the brown stuff is aromatic compounds, I'm going to call it. You've heard the term aromatic? You're cooking, you say wait till you can smell the aromatic. Okay, so aromatic compounds that are formed in Maillard reactions. It's French, not Maillard reactions. Actually, do you guys even know who Alton Brown is? Okay, never mind. Good Eats, good cooking, fun cooking show. Anyway, maybe I'll show you a video sometime. Anyway, here's something that kind of shows you things in Maillard reactions. You're not going to need to know this, but I do want to talk about them really quick. So we talk about aromatic compounds. These are the compounds that have the flavors. Okay, and here you've got some of the flavors that happen. Notice that these are aromatic in terms of when we think about smelling them, but also in terms of organic chemistry, aromatic means something. It means these double bond, single bond structures, all right, that occur. And you get these things when you have a carbohydrate, okay, here this author just put sugar, and you have like an amino acid, you've got an amine group here. So you've got proteins and carbohydrates and one other thing that's related to phase changes. Energy, right? Heat. Okay? All right, so these form when there is a carbohydrate, and there's some carbohydrates in meat. Okay, your muscle, you store carbohydrates in. The same thing for animal muscles. When there's a carbohydrate, a protein, and temperatures over 120 degrees Celsius. Okay. At what temperature does water boil? Water boils at 100 degrees Celsius. Okay, so that's important. If you take a piece of meat like this and you drop it in boiling water, do you get those great tasty browning reactions happening? You don't, you just get some gray meat, right? Okay. And so if you're making a stew, you'll probably do this browning and then cut the meat up and then throw it in. Depends on what you're doing. I'm actually vegetarian, by the way, so, but I haven't always been. So we need that 120 degrees, and so that's important for water, and it's important about phase changes. We need to get, if we're going to get this color, the meat has water in it too. We have to boil off enough of that water, or that liquid. If we were braising and we had liquid, we'd have to boil off that liquid, and once we boiled off the liquid, then we could start getting our browning reactions. But not until all liquid's gone. So if we think about water, and we think about phase changes for water, we can do a little graph. And this is it's not a phase diagram. A phase change diagram is something different. But we can do a heating curve for water, or any substance. Any substance is going to look like this. So we've got heat. They're not going to have the same temperatures. Over here, we're going to have maybe 0 degrees Celsius. Over here, we're going to have 100 degrees Celsius. All right, and so I'm going to start out, if I go to my freezer and I pull some ice out of it, It's probably a little bit wet because my daughter's left the freezer open again. Okay, but I'm gonna go ahead and I start heating that up. It's gonna heat and the temperature is gonna go up and up and up until it gets to 0 degrees Celsius. Before it's at 0 degrees Celsius, this is ice or it's solid water, right? Once I get to 0 degrees Celsius, what starts happening? Okay, the temperature is going to stop changing and it's going to start turning to liquid, right? And so what I'm going to get here is I'm going to get a flat line at 0 degrees Celsius. If I have a drink and it has ice in it and it's well mixed, it's all 0 degrees Celsius. Okay, the ice is at 0 degrees Celsius. The waters or liquids, well, it's mostly water, whatever you're drinking as well, is 0 degrees Celsius. All right, so this is going to be solid plus liquid. All right, and then once it's all liquid, then the temperature can start going up. So then the temperature will go up until I get to 100 degrees. It's all liquid here while the temperature is going up. And once I get to 100 degrees, what starts happening? Okay, what was that? It starts vaporizing, right? We start making a gas. And while it's making a gas, it stays at 100 degrees until it's all gas. That's supposed to be a flat line. All right, I'm actually trying to represent how long that line is, how much heat you have to put in to turn it into a vapor. This is going to be liquid and gas. And then once all of it is gas, then the temperature can start going up again. Okay, that's what the heating curve looks like roughly. So let's think about this here. Well, it takes a lot of energy to take that liquid from and turn it into a gas. Why is that? Think about it at the molecular level. Show me what liquid is with your hands. Liquid looks like this, right? Kind of rolling around. Then what do I have to do to make it a gas? I have to fully separate these things. I have to break all the bonds. There's kind of a lot of heat in terms of turning it from solid to liquid as well. I have to break some of the bonds, right? Like this. I have to break some bonds so that this can happen. But I have to break a lot more bonds to break it apart like that. That's why it takes so much heat. I didn't have many people in the previous class. How many of you have ever had a steam burn? What's a steam burn like? You heard about you got steam, but what is it like? What does it feel like compared to other burns you've had? It hurts a lot. Okay, I burned myself with the iron, with a steam burn, steam off the iron. It hurts a lot. And why it hurts so much is you've got steam up here, right? Get steam anywhere in here. It doesn't really matter where you're in here so much. But it releases all that heat onto your hand or arm or wherever you got hit with steam. So much heat here, it all gets released onto you, and that's what, so you're getting burned really hard and there's a lot of damage. So that's why steam burn hurts so much. Okay? But also when we're cooking, most of your time is going to be spent heating and getting the water to boil off if you're trying to get browning reactions. So I have a crispy onions and lentils thing I do, and I boil the onions in oil. So it goes on outside, so the house doesn't smell like that. But I boil them in oil, and the onions sit there, and the onions are there, and they don't brown, and they don't brown, and they don't brown, and they don't brown, and then they go from brown to burnt really fast, because what they're doing is they're sitting in the oil, and the water's getting boiled off, and the water's getting boiled off, and the water's getting boiled off, and it takes a long time. And then once for most of them the water gets all boiled off, then suddenly the temperature can go up a lot. Does that make sense? It's not exactly all water. It's not quite as clean as this, but that's the way to think about it. Questions on the heating curve? Okay, it's important to know what that heating curve looks like. I want to give you a feel though, because I've drawn this, right? And I've actually drawn it pretty accurately. But I want to give you a feel so that when I'm trying to draw this, this is 5 times as much heat as that. You go from 0 degrees water to 100 degrees liquid water. This is 5 times as much heat. I want to give you a feel for that using the actual numbers. Okay, and this will give us a little bit of practice. We'll end up with a little bit of practice with dimensional analysis. So here we have a table from your book. I saw this table last night, and my wife, who's also a chemist, although now she does web development, I said, they put the phase change numbers and the specific heat numbers in different units. And she said, oh, that's pretty typical. And I feel like that's horrible. It's a crime. They're robbing you of being able to see the difference, right? Because they're in different units. So let's put them in the same units. So remember, your specific heat capacity here, your specific heat actually, that's the amount of heat required to raise 1 gram of water, that much water, okay, 1 degree Celsius. So that much water, 1 degree Celsius. Let's go ahead and take this heat of vaporization, which is in kilojoules per mole. Let's put it into joules per gram. Okay, so we can compare the two. So I'm going to start off with, I've got 40.65 kilojoules per mole. Okay, that's my units for my heat of vaporization, how much heat it takes for this, it's a mole, take a mole of water and separate all those water molecules. How much, how am I going to get this, how am I going to do this conversion? What should I do?
You can start with the kilojoules.
Okay.
Either 1,000 joules and 1 kilojoule.
1,000 joules and 1 kilojoule. What goes on top?
1,000.
Yep. 1,000 joules over 1 kilojoule. Really encourage you to use these units because then I can cancel those units. Remember, 20 IQ points lost up at the board. But this saves me. Okay? Super, super good system. Okay. What am I going to do with a mole? Okay, not 1 gram is 1 mole, but I can use the molecular weight here, right? Right, so remember if we have 2 hydrogens in a water and we have 1 oxygen, the hydrogens, if I look at the periodic table, are going to be about 1.01 grams each, right? The oxygen is going to be about 16.00, right? So this is times 2, so it'll be about 2.02 plus 16 is going to give me 18.02, right? And so over here, I'm going to say 1 mole, I put the mole on the top because I want it to cancel, is equal to 18.02 grams of water. I'm going to cancel that, and then I can multiply across the top and I can divide by the bottom. I did it last lecture, so I know that it comes out to be about 2,220. My units are, that's left, joules per gram. And so it takes about 500 times as many joules to vaporize a gram of water as to raise it 1 degree Celsius. So if I want to raise the temperature of water 100 degrees Celsius from just melted ice to just about to boil water, you can do this in your head, but about 5 times as much energy. So a ton of energy to vaporize water, okay? Super important. In cooking, biology, all sorts of things. Okay, thanks guys. You guys have a good day. I will see you on Friday. Remember